Hello, AP Chemistry 12. This is Mr. Chan, and this is the last lesson in terms of the AP reaction kinetics. And what I wanted to focus on in this particular lesson was the Arrhenius equation. Now, the Arrhenius equation is named after a physical chemist called Svante Arrhenius, and he noted that for most reactions, the increase in rate with an increase in temperature is a non-linear relationship. Now, you folks experienced that when you did your rate law lab, or you did your rate lab. Notice when you did your rate lab and you plotted the, how fast the thing dissolved over time, you notice that it was never a really straight line graph. Some of you might have had an exponential curve. Some of you might have had an S-shaped curve. So that was one thing that Arrhenius noticed. And so what he theorized is that since the rate is non-linear with temperature, he found that most reaction rate data obeyed an equation based on three factors. Number one, the fraction of molecules with sufficient energy, the number of collisions per second, and the fraction of collisions with correct geometry. These three factors were incorporated into the Arrhenius equation, where K is equal to A times the inverse natural log raised to the power of the negative activation energy divided by the universal gas constant and temperature in T. Now, what's the significance of this experiment? Again, or this equation? Again, if we integrate this particular equation, what happens is we get a straight line graph. So the straight line graph shows us this. So if we take the natural log of the rate constant on the y-axis and plot it against the inverse temperature in kelvins, what we get is we get some constant value. And this constant value is the activation energy for this particular reaction. Okay, so again, what does the integration do? It just changes a graph that looks kind of weird like this and creates a fairly linear graph in which we are able to plot data points and be able to get a straight line graph. And in this case, we are able to figure out the activation energy. Now, we can use the Arrhenius equation to evaluate the activation energy in a non-graphical way if we know the rate constant at 2 or more different temperatures. So what we have is if we had one equation for temperature number 1, here at temperature number 2, if we were to combine the two, we would get this particular equation. Now, again, this is given, and all you need to know is how to use it. And using this particular equation, where you take the ratio of the rate constant for reaction 1 and the rate constant for reaction 2 and take the natural log of it, what you are able to do is you are able to calculate the activation energy of that particular reaction. Because going back to reaction kinetics, remember, activation energy doesn't change with a change in temperature. Now, depending on which reading you take, so let's say you take a look at your Hebden. Hebden gives you an example of how to use the Arrhenius equation, okay? And they talk about finding the activation energy. Now, the one thing you will notice is this. Notice here, why do I have K2 on top, K1 on the bottom? Notice the slight difference. Notice, because I have K2 on top, K1 on the bottom, my activation energy constant here is negative, and my T2 and T1 are different. Okay, they're flipped. So when you're trying to reconcile this reading with what I gave you, please make sure you're aware of the slight difference, Okay, notice here, my activation energy is a positive value here, and my T2, T1, okay, is, sorry, and my K1, K2 is inverse, okay, flipped from what was in the Hebden book. So please be aware of that, all right? Same thing if you are looking in your Zoom doll. The Zoom doll talks about it as well, okay? They give you the Arrhenius equation, the integrated Arrhenius equation, and they talk about how you use the Arrhenius equation to calculate the activation energy. Now, notice here, you might say, well, Mr. Chan, why is there no negative value here? Is because the temperature was flipped. In this particular equation, it's T1 minus T2. So please be aware of the slight difference in the two equations, in the two reading packages that I've given you. All right? All right, one final thing. Now, remember when we did reaction mechanisms? If we went back to the very beginning, reaction mechanisms, okay, let's see, potential energy diagrams. Let's see, scroll down, scroll down. Okay, remember reaction mechanisms, there was either an elementary process, where it's one step, and a ternary process, or a termolecular collisions, where you had multiple steps. Now, we can apply rate laws to those as well. Now, for elementary steps, if we know that a reaction is an elementary step, or it's just one step, then we know it's rate law. The rate law of any elementary step is based on its molecularity. So the number of molecules that participate as a reactant in an elementary reaction. So the key word here is this. So for elementary steps, the rate law is based upon its molecularity. So in this case, for the first example, since there was only one reactant, the rate law is K is equal to the concentration, rate is equal to K times the concentration of A. For here, where you have two reactants, the rate law is rate is equal to K concentration of A times concentration of B. Now, if we take a look at rate laws for multi-steps, for multi-step reactions, because there's a slow step, it is the slowest step that determines the rate and the rate law for the overall reaction. So in this particular step, let's say, for example, we have step 1, step 2. The net reaction is NO2 and CO, gives you NO and CO2. Since step 1 is the slow step, the reactants in the slow step determine the rate law for the overall equation. Okay, so that is rate laws for multi-step mechanisms. Now, what we're going to do is we will stop it here in regards to today's lesson. If you take a look at your notes, it says, what if the slow step is not the first step? What I'm not, because this is not part of the AP curriculum, okay, I will not be going through it, but you can read through it if you're interested. And it is explained in the Zoom doll text, probably near the end. I think if we take a look, probably near the end of the chapter. Okay, so if you are interested in going through that, by all means. But all you really need to understand is rate laws is to this particular page here. All right, folks, thank you. Have a good day. Bye-bye.